Okay, so now moving on to section 3.4, Introduction to Radicals. So this is not really an extension because you need to know this in grade 10. What we're talking about here are going to the exponents of irrational numbers. So the exponent is an irrational number. And review what an irrational number is. It's basically a number that you can't put as a fraction because it goes on forever and doesn't repeat. So an example of that would be the number pi. So you should know pi is 3.1415, etc., etc. So it keeps going on forever, right? So you can't put it as a fraction like something like 0.25. You can put it as 3 over 4, or that's wrong, that's 0.75. 1 over 4, right? So, but you get the idea. So you can't put a rational number as a fraction because it goes on forever and doesn't repeat. The other definition you kind of need to know that we're going to be talking about here is a radical. So what's a radical? So let me try zooming in here and move this to the right here. So we're looking at this section on the right here, and you can see all the definitions are highlighted in your textbook. Um, and again, we're doing this a little bit differently. We'll go over the textbook notes and see if that is better or worse, or we'll see how it goes. So a radical is this entire thing, okay? The whole thing is known as a radical. So what's in a radical? First of all, you have the radical symbol, the little check mark here, okay? So, and inside the check mark is going to be known as your radicand, and on the left side is going to be your index, okay? And we'll go through this a few examples how you get that. So here what they have is they're generally telling you how do you go from the exponent form right here, x to the power 1 over n, to the radical form here where n is on the outside. And I think we went over this in a previous notes section, but basically all you do is you swing the denominators. The denominator becomes the index, right? So it goes onto the outside on the left, and then you put the little radical sign symbol, the check mark, and the numerator stays on the right. So here there's no 1 here, but it's 1 by default. It's an invisible 1. So an example here, let's go over here. So it's 3 to the power 1 half, multiply by 3, 1 over half. And what should you think? Okay, now we're exponent law, we're adding, because when you're multiplying it at the same base, you add the exponent. The denominator and the fraction is the same, so we can just add the 1. So 1 plus 1 is 2, and 2 over 2, and then just show that step, 2 over 2 is just 1, so that's why it just equals 3. Okay. So here what they're doing is they're just showing you that you can also go the square root of 3 times square root of 3 is equal to 3, right? Because when you're multiplying the same square root, you just get the number, right? And they're just showing you that they equal the same thing. So 3 to the power 1 half is the same thing as square root of 3. Okay. Now you may be asking, okay, 1 is not there because it's 1 by default. What about the 2 in the bottom? We swung it to the left as the index. So by default, if there's no number here, there's an invisible 2, right? And if there's no number on the right, it's an invisible 1. So this is just a square root of 3. Okay, we'll look at that. Well, we'll look at one more example at the bottom here. So maybe I'll get rid of myself because I'm kind of blocking the view. I think I'm gone. I'm not exactly sure, but so power can be expressed in the radical form, and here's a general idea of what's going on here. So x to the power of m over n, and now what they're doing is, oh, I guess they had separated it here differently to show you the step. But basically, you see the n on the bottom, it's the index. You swing it to the left, right, and put the radical sign, and the m stays on the outside here. So there you go, simply like that. You can also write it this way as well, if you don't want to write the brackets here, where n is on the side and m is on the x. So both of these are the right way to write it. Okay. So they show you, and to go backwards, you just do the same steps in reverse, right? So here you got this radical where the index is 5 and the exponent here is 3. So what you're doing is you swing it back to the right. So the 5 goes under as a denominator, and then you just put it 6 to the power of that fraction. So 6 over 5 over 3, 3 over 5. And if you want to, you could put a decimal form, or you just leave it as 6 over, to the power of 3/5. Okay. Okay, so let's just go through all these examples in this section. There's about, I don't know, six examples, so it shouldn't take us too long. So I'm going to zoom in onto this side and on Okay, there we go. So top left, so example number 1, convert from a power to a radical. So these are exponents of power, and the exponent form is the same thing here, to an equivalent radical. So how do we do this? We just talked about it. The 2 swings to the left here, and the 1 stays there. Remember, the 2 and 1 is going to be by default, so you don't need to write it. So here you can see they just swung 2 to the left and 1 here, so square root 64. Here, again, this example B, you swing the 4 to the left, the index, there we go, and the 3 stays there. And there you go, you're done. That's it, simple. And they're just showing you could write it this way as well. The form I usually write it is like this. It just looks a little bit neater with the brackets as well. You can kind of tell that it's on the outside, but this is fine too. Okay, now here, what are we going to do here? So this 1/3 applies to the whole thing, right? So you want the entire thing, whatever's inside here, to be the radicand, so AX. And the 2 is just stuck on the X, so you have to write it this way. You can't write it on the outside, because if you put the 2 on the outside, it's going to be like we're squaring the whole thing, but the square only goes to the X. So there we go. Okay, example number 2 says convert from a radical to a power. So now going backwards. How do we go backwards? Okay. So to go backwards, you're just going to swing the index to the denominator position in the fraction. So we can look here. All they did was they swung it to the bottom, so it's going to be 4 to 3/4. Right? So you don't really need to show this step, just 3/4. Again here, all you're doing here is swinging the index to the bottom of the 4, so 3 to the 4/5. And here, what are we doing here? This might look confusing, but remember, if there's nothing here on the left, there's an invisible 2. So the 2 gets swung under the 3. So s to the 3 halves, right? And there we go. So let's try to go to the top here. So this section, example 3, provides some new information. This is going from mixed radicals to entire radicals. So what is a mixed radical? Here's a formal definition: the product of a rational number not equal to 1 and a radical. Okay, so like right here, look at A. This is a mixed radical because the rational number, the whole number on the outside, is 2, and the radical is right here, so square root 5 in this case, right? So you got those two portions. It's mixed because you got the number on the outside, the rational number, and the irrational number. Okay. The other definition you need to know is an entire radical. Formal definition: the product of one and a radical. So basically, an entire radical is basically when there's no rational number on the outside on the left here. So look how there was a 2. So instead of having that, you can have everything in the radical sign, or this is also works too, where you have this whole thing is a radical as well, right? But the entire thing needs to be a radical, where this is a mixed radical, for example. So anyways, we got those definitions out of the way. So how do we go from 2 square root 5, this mixed radical, to an entire radical? We need to put this 2 inside the radicand. But you can't simply just put the 2 in, because think of this check mark as a kind of like a barrier. So whatever you this check mark says to do, you have to do that before you go in. So for example, there's a invisible 2 here. We're finding the square root of 5. So to put the 2 in, you have to multiply it by 2. So 2 times 2, right? So we stuck that in there. So 2 squared, which is 4. And then you multiply that 4 with a 5, which is 20. So maybe that was confusing. Let's look at another example here. So part B. So we want to get this mixed radical as an entire radical. So how do we stick the 5 in there? So remember there's an invisible 2 here. This thing is squared. So to get the 5 in there, you need to square the 5 first. So here, that's what they're doing. So they're doing a separate step, so you can see. So to put the 5 in, you have to square it. So 5 times 5 is 25. And now we have 25 in there. Now you can multiply the 25 with 11. So 25 times 11 is 275. So this mixed radical, right? 5 is a rational number, and the radicand 11 is the same thing as the entire radical of square root 275, right? Hopefully that kind of makes sense. So let's look at example 4 here. So now it says express each entire radical as an equivalent mixed radical. So now we're going backwards, or the other way around. So we got the entire radical, but we want to pull out like a rational number and put it onto the outside. So you just need to think a little bit more backwards here. So how do we get rid of a number and put it on the outside? You need to find a perfect square in this case. So this thing is to the square, right? The square root. what's a perfect square multiplied by another number that gives you 27? So you have to go through it. Just think about different numbers and say you get 9 times 3. So we went over a perfect square. So 9 is a perfect square because 3 times 3 is 9. So that's why I have 9 times 3. So now we can pull out the square root of 9, which is 3. And you just leave the other number in there. So it's 3 square root 3. That's how we got it. So let's try 2 more examples if that didn't make any sense to you. So zooming in a little bit here. So we got our square root 50 here. So now you're going to think about what's a perfect square multiplied by another number that gives you 50. And then you could think, okay, 25 times 2 gives you 50, right? So because 25 is a perfect square, so what factor multiplied by itself gives you 25 is 5. So we could pull out the 5. And the 2 we said, 25 times 2, the 2 just leave in there. Okay, there you go. Okay, 48, same sort of thing. What perfect square multiplied by another number gives you 48? So if you think right away of 16, so say you say 16 times 3, okay, and then you know 16 is a perfect square because 4 times 4 is 16, and you can pull out the 4 and leave the 3 in there, right? Or say you just thought you really need to just think about 2 numbers. So instead, say you didn't get that, you didn't think of 16 times 3, you just thought about 12 times 4. Okay, well that's fine, but 12 and 4 are not perfect squares, so there's additional step you need to do here. So first they split into 4 times 12 inside of the radical, and then what you'd have to do here is you have to go a little bit further, right? Because well, I guess you could say 4 is a perfect square, so you can pull out the 2. That's what they did. They pulled out the 2, but you can go further with a 12 because a 12 you can pull out another perfect square. So 4 times 3 also gives you 12. So you can pull out another 2. So when you pull out the second 2, then you go 2 times 2 is 4. So then you get the same kind of answer here. It's just an additional step. So two numbers that equal 48. 4 times 12 gives you 48. 4 is a perfect square, so you can pull out the 2. Then you're left with the 12 inside. Split the 12 into 4 times 3 over here. And then we can take the 2 out of the 4 as well, because the second 4 that we got is a perfect square. So then once you pull out the 2, you have to multiply it. 2 times 2 is 4, and left with a 3 inside. Hopefully those 3 examples kind of clarify it. Going from entire radical to mixed radical, and at the top here, example 3 was mixed radical to entire radical, going both ways. Okay. Okay, let's look at example 5 here. You might get a question on the test that says something like this: order these radicals from least to greatest. So how do you compare these radicals? Well, one way is obviously just use your calculator, punch it in, and see which one is what kind of decimal answer you have. And that's what they did here in a method too. So they converted all of them into decimals just by typing it into your calculator. Square root of 18 times 2 will give you that decimal. Square root of 8 gives you this decimal. Approximate and this, etc. So once you get the decimals, you can just order them least to greatest, right? The other way to do it, if you didn't want to use your calculator, is just convert everything here into entire radicals. So maybe I'll zoom in a bit. Give me a second. There we go. Hopefully this is clear. So you can see that the 8 here is already entire radical, and square root of 32 is entire radical. So 2 are already done for us. We just need to convert these 2 mixed radicals into entire radicals, and you can compare it. So remember how to change this to a mixed radical? You need to stick the 2 inside of the square root sign. So how do you stick it inside? You have to square it first. So that's what they did. So they squared the 2, you get 4. And then once you have 4 inside of there, you multiply 4 times whatever's inside whatever's the radicand already. So 4 times 18 gives you square root 72. The 8 was already done for us, so like I said. So the 3 to put inside, you're going to square it first, which is 9. And that's what they're doing here. 3 times 3 is 9. And then you multiply by what's inside there, 9 times 2. So the entire radical is 18. Square root of 18, and you get square root of 32. So once you have these numbers in entire radicals, then you can just compare it from biggest to smallest, right? So the order is square root of 8, and then square root of 18 is bigger, square root of 32, and square root of 72. Then we have the order. We're done. And then you can basically get the original answers here. So they also said this was square root of 8 was originally square root of 8, and then this was the mixed radical, etc. So just reconvert it to the original stuff. Okay. And there we go. So let's go into example 6 here. I think this might be the last one. Okay, so example 6, it's a word problem here. And let me just make sure this is lined up okay. Okay, I think it's fine. So with word problems, I think a lot of people are confused when they get to word problems, at least based off last day's homework. When you're on a word problem, just make sure that you're dissecting, or not dissecting, extracting the vital information. So the stuff that's important. Basically what I'm saying, when you have a word problem, there's a lot of stuff that's just confusing and you don't really need to know. Like the Highland Valley Copper Mine is near Logan Lake, BC. You don't really need to know that sentence, but I guess it's just kind of interesting because now you know that there's a copper mine near Logan Lake, BC, I guess. But anyways, you just need to pick out, okay, we got our volume cubed, we have 5 days, and we're looking for edge length. So the most important thing when you're looking at a word problem is look at what they're trying to find. They're trying to find the edge length. So I haven't even read the question yet, and I know that it is trying to find an edge length. Let's just read the entire question first. So in 2016, the mine produced a daily average amount of copper great enough to fill a cube with a volume of 36 meters cubed. So every day that they're mining, they fill a volume of 36 meters cubed. Remember, volume is always cubed because we're trying to fill in a space, right? We're trying to fill a volume, right? So 36 meters cubed. And that's one day that they fill that much. In 5 days of copper production is cast into a cube. What is edge length? So they're asking you what is the side of the cube, right? So in one day they did 36 meters cubed, but they're asking you about a bigger cube, the cube after 5 days. So if they make 36 meters cubed, how much do you get in 5 days? You just multiply. I'm pretty sure most of you kind of just said that or guessed that. So 5 times 36 centimeters cubed, and it should probably be meters cubed. I don't know why they changed it to centimeters cubed, but 5 times 36 meters cubed will give you 180 meters cubed. So we got our big cube now of 5 days, 180 meters cubed. So how do we find the side length after 180? We have our cube size. Remember, you have to know the formula of a cube, right? I kind of stuttered there, but so side length times side length times side length will give you the cube volume, right? So that's just a formula you need to remember, and it doesn't matter what side it is because in a cube, all the sides are the same. So here what they did is they got that 180 that we got, the volume of the cube, and is equal to this, whatever the side length is, cube times 3, right? So if the side length was 10, 10 times 10 times 10 would give you 1,000. That would give you 1,000 meter cubed size, right? So you know, obviously this is 180 is less than 1,000, so we know that side length is going to be less than 10 as well. Yeah. So how do we get rid of, we're trying to find S here, how do we get rid of the 3? We basically cube root it. So you do the cube root on one side, that means you have to do the cube root on the other side. So cube root of 180, and right here you can just find this on your calculator. You don't really need to do it out because I don't, it would be pretty hard to find this decimal answer. So you're gonna have to use your calculator here, and then you get 5 plus 6 and so forth. Another example, what they did is they just put it to the opposite fraction here, or the reciprocal fraction, 1/3. You have to do the same thing here, and then you put that in. Same sort of idea. I would just do the one on the left. Just stick to one method. They both give you the answer here. So the side length is 5.646. And remember, if you have a word problem, you need a kind of a word answer, a sentence answer. The edge of the cube would be approximately 5.6 meters long. Okay, so yeah. Okay, so let's just look at the key ideas section here to go over the key ideas of the section we went over. You should know how to go from an exponent form to the radical form and how to go back and forth. Remember swinging it to the index value to the left and keeping the numerator on the right. Know how to go from entire radicals, where everything is in the radicand sign here and there's no rational number on the outside on the left, to the mixed radical form, and how to go from mixed radical to entire radical. So we just talked about that. You can order radicals and irrational numbers using different methods. So if you're told to order them, you can use the calculator and put them all into decimals and then order it that way. Or you can order all the mixed radicals into entire radicals, and when you have a series of numbers are entire radicals, then you can directly compare them as well. Okay. Oh, there's a cool fact here. Did you know the world's oldest known copper mine is at Timna Valley, Israel? Excavations have found evidence of smelting activity dating to the earlier Iron Age. Oh, that's pretty cool. Interesting. Okay, and that's about it. So that's the chapter. I'll post the homework in the homework section as usual. So today we have just that section, and in another video I'll go over a project that we're going to be doing. Okay.